SpaceX just pulled off something that, until recently, sounded more like science fiction than engineering. For years, watching two Falcon Heavy side boosters land at the same time on solid ground felt like the peak of what rockets could do. It was the kind of moment that made people stop scrolling, stand still and just stare at the screen. But behind the scenes, engineers were already chasing something bolder, something that would make even that achievement look ordinary. They were quietly working on a way to land both massive side boosters on a single moving drone ship in the middle of the ocean. This isn't just about showing off. It isn't about creating another viral video moment. It's a calculated answer to a problem that has been quietly eating into the company's schedule for years. And the timing matters. When NASA shifted its lunar focus in March 2026, moving away from the original Gateway concept and toward building an actual surface base on the moon, the math changed for everyone involved. Suddenly, the demand for heavy lift launches went up. The pressure on recovery ships went up, and SpaceX needed a way to do more with less. That's where this dual landing concept comes in. By mastering the ability to recover both boosters on one ship, SpaceX can free up its other maritime assets for something even bigger, supporting the rapid scaling of Starship version 3. In simple terms, they're solving the Falcon recovery puzzle so they can pour everything into the Moon and Mars missions ahead. The engineering risks are huge, but if it works, it could rewrite the economics of spaceflight forever. The first real signal came quietly. In a recent post, the company's vice president of launch confirmed that Launch Complex 39A is now officially shifting into a pad focused mainly on Falcon Heavy and Starship operations. To most people, that update looked like a small scheduling note. In reality, it was a window into a much larger strategy already in motion. For years, 39A at Kennedy Space Center had been one of the busiest Falcon 9 launch sites in the world. It carried commercial satellites, Crew Dragon astronauts, and countless other missions, but that role is now changing. Routine Falcon 9 launches from Florida are increasingly being moved over to Space Launch Complex 40 at Cape Canaveral Space Force Station. On the surface, this sounds like simple housekeeping. Underneath, it's a complete reorganization of the company's East Coast launch system. By relocating standard Falcon 9 missions to SLC-40, 39A gets freed up for the vehicles that demand more infrastructure, more space, and more preparation time. Falcon Heavy, Starship. The rockets tied directly to the company's deep space ambitions, national security contracts, and next-generation heavy lift missions. And with fewer Falcon missions needing offshore recovery, there's no longer a need to keep two fully active drone ships running on the East Coast. One ship used cleverly can handle what's left. While many Falcon 9 boosters keep returning directly to land, that leaves the second drone ship available for something much bigger: Starship logistics. The vessel could be reassigned to transport massive Starship and super heavy hardware from Texas all the way to Florida. But there's a deeper problem this solves, one most people outside the industry never see. In the past, a Falcon Heavy mission that needed downrange booster recovery could throw the entire Florida launch schedule into chaos. Because Falcon Heavy uses two side boosters, sea landings traditionally required both East Coast drone ships at the same time. That meant deploying the full fleet far offshore, leaving no recovery ship available for anything else, and that came at a real cost. A round-trip journey from Port Canaveral to the landing zone and back can take nearly a week, depending on the mission profile and sea conditions. One Falcon Heavy launch could effectively freeze every other Falcon 9 ocean recovery mission for days, choking the launch cadence and piling pressure on the entire manifest. By mastering double booster recoveries on one drone ship, the company can support Falcon Heavy missions without sacrificing the rest of its launch tempo. Instead of tying up two autonomous platforms, one vessel handles the complex recovery while the rest of the fleet stays available. The result is bigger than it sounds. Falcon Heavy no longer has to interrupt Falcon 9 operations. Heavy lift launches can happen alongside routine commercial missions, Starlink deployments, and crewed flights, all without the old bottlenecks getting in the way. But none of this comes easy. The breakthrough carries serious risks, and leadership has openly admitted that. The vice president of Falcon and Dragon programs warned that there's a much higher likelihood of losing a side booster, or even two, and damaging the drone ship during a dual recovery attempt. That one statement alone tells you just how technically demanding this operation really is. One of the biggest challenges is deck space. The two boosters have to land far enough apart to avoid colliding, but close enough that both stay within the safe range of the platform. Any small navigation error could turn a perfect mission into a catastrophic collision at sea. Then there's the thrust problem. Each booster uses a Merlin engine during landing, generating around 190,000 pounds of thrust, the equivalent of over 86 tons of force pushing downward. When the second booster descends, its exhaust can create powerful wind pressure and turbulence right next to the first booster already standing on the deck. That could destabilize the earlier landing, or worse, blow it over entirely. The heat and pressure could also damage sensitive systems on the already recovered rocket. And then there's the ocean itself. The sea remains one of the most unpredictable variables in the entire operation. Weather can be forecasted but never fully controlled. Once two heavy boosters are standing on a single deck, the ship becomes far more sensitive to rolling waves, shifting winds, and platform movement. Even after a successful touchdown, the rockets have to stay stable until the crew can secure them. A sudden wave or strong gust could cause sliding, leaning, or in the worst case, tipping over. But unlike the weather, most of these risks can be engineered around, and that's where SpaceX has always excelled. The most obvious mitigation is launch discipline. They can simply avoid poor sea states by applying stricter weather criteria before liftoff. If conditions are marginal, the mission gets delayed rather than risking expensive hardware. To reduce engine plume disturbance during recovery, they can also use staggered landings where one booster touches down first, followed by the second a moment later. It's the safer approach because it lowers the chance that the second booster's exhaust destabilizes the first. But that solution brings its own challenges. The second booster has to stay airborne longer, burning extra propellant while keeping flawless guidance control. Timing becomes everything. The descent has to be choreographed precisely so the second landing happens without damaging the platform or the already landed rocket. Before this whole concept becomes routine, the recovery fleet itself will likely need upgrades. The drone ships may need structural reinforcement to absorb the combined mass and landing loads of two rockets arriving in quick succession. Guidance and navigation systems will need to become even more precise, coordinating two independent returning vehicles with a moving platform at sea. Behind all of this, advanced simulations are likely being used to refine descent profiles, model the interaction of dual engine plumes, and predict how the barge will behave under real ocean conditions. So what does this all mean for NASA? The answer goes far beyond saving boosters. With the Lunar Gateway program being scaled back and the agency placing greater emphasis on direct surface logistics, NASA increasingly needs rockets that can send large cargo straight toward the moon. That means bigger landers, heavier science payloads, power systems, and rover-class missions. And this is exactly where Falcon Heavy becomes strategically important. Today, Falcon Heavy remains one of the very few commercial rockets capable of sending massive payloads directly onto a trans-lunar injection trajectory. Instead of parking hardware in Earth orbit first, it can perform the high-energy push toward the moon in one clean mission profile. A perfect example is the Griffin lunar lander, which was selected to carry NASA's Viper rover. Falcon Heavy is meant to handle the trans-lunar injection burn, allowing the lander to save its own propellant for the descent and braking phases. That hugely increases mission flexibility and payload capability. But these missions are demanding. The payload mass and energy requirements can be so high that Falcon Heavy side boosters may not retain enough fuel for return to launch site landings, forcing ocean recoveries instead. That's exactly why the new single drone ship dual landing capability matters so much. If both side boosters can land on one vessel, the second drone ship could be freed up to attempt recovery of the center core. Historically, the center core has been the hardest booster to save because it flies the most punishing trajectory and burns the most propellant. Recovering all three cores would be a massive breakthrough in Falcon Heavy economics. At roughly $150 million per launch, reusing every booster dramatically lowers hardware replacement costs, saving somewhere between 70 to 80%. It also increases fleet availability and helps the company offer more competitive pricing for lunar cargo missions, defense launches, and other high-value contracts that have traditionally favored expensive, expendable rockets. In simple terms, this is bigger than just saving rockets. It means NASA could gain access to a powerful, increasingly reusable heavy lift vehicle capable of delivering major lunar payloads at lower cost and higher cadence. Exactly the kind of capability needed for a sustained return to the moon. But here's the part most people miss. The real reason for this breakthrough isn't just about Falcon Heavy, it's about Starship. One of the legendary drone ships has officially been pulled from the Falcon landing rotation. It's being repurposed as a heavy transport platform for Starship version 3, and once you look at the hardware, the move starts to make complete sense. The ship is a large, robust barge converted from an existing platform, giving it a wide, flat deck capable of withstanding the mass and impact of very heavy boosters. For the super heavy booster used in Starship version 3, the ship needs both strength and low flex. Its hull and deck already meet that requirement for Falcon-class loads, with headroom for the bigger Starship-era hardware. It's equipped with 4 powerful azimuth thrusters and upgraded electrical drive systems that let it hold an extremely tight position in the Atlantic, even in moderate seas. For Starship's high speed, high-energy downrange drops, that ability to park the ship exactly where the booster will arrive is critical. Small position errors would otherwise make safe landing impossible. Then there's onboard power. During its Atlantic upgrades, the ship received 6 diesel generators along with enhanced electrical and control systems. Those were originally intended for long-duration Falcon recovery missions, but they create real room for future Starship needs: lighting arrays, chilled systems, powered access structures, support equipment, and potentially even hardware tied to future catch or transfer operations. And finally, it already functions as a floating communications hub. The ship carries Starlink connectivity, tracking antennas, cameras, and sensor systems used to monitor incoming boosters in real time. For Starship version 3, that network could expand into a full telemetry and structural monitoring station, measuring landing forces, deck movement, booster condition, and recovery performance. That transforms the ship from a simple drone barge into something much bigger, a mobile offshore logistics node connecting Texas, the ocean, and Florida launch operations. So while many people see this as just a Falcon fleet reshuffle, the truth is much deeper. Old Falcon infrastructure is quietly being converted into the backbone of the Starship era. And the moon, along with everything beyond it, is the real destination.